So this is problem number 8. And instead of just posting the solutions, I'll also post how to get the solutions to these questions. So you've read this, I hope. And we're asked to find an equation that models the percentage of carbon-14 in a sample of wood. Consider the time 0 that there is 100%, and that at time 5,730 years, there's only 50% of the carbon-14 isotope remaining. So recall that an exponential equation looks like that. We could also write it where x equals t, because we're basically looking at some initial value times the rate raised to some t time. Years, days, months, but in this case, years is the unit. So equation that models this, we need to find out some pieces here. We do know that 50% is left after t time equals 5,730 years. So we can write in the information we do know, and we'll figure out what to solve, what's missing. So I write in that 50%, or let's say 50 grams or whatever amount, is equal to 100%. This is a B, our base, raised to some time. The time is 5,730 years. So half, this is half of 100. I could use 40 and 20, I could use 10 and 25 and 10, doesn't matter. If we're solving for B, that's the only thing that's remaining, divide both sides by 100, and I get 1/2 is equal to B raised to the 57/30th power. And you recall how to undo powers. This is a power equation. Undo powers, we raise to the inverse power. So you'll raise 1/2 to 1/5730. And then you'll get B equals, and in this case, I believe the decimal is kind of long. Approximately. We'll stop there. So this is B. Now going back to my equation, I needed to write an equation that represents this information. So I can write it as, because this is my variable, or I can write it as the amount is equal to 100% times this value raised to some t time, or x, my input. So this brings us to our second piece, which is part B. A piece of wood contains 48 37/100% of its original carbon-14. According to this information, approximately how long ago did the tree that it came from die? And then what assumptions are we making, and why is this answer approximate? Well, so here's the original equation. With 100% multiplied by this amount, so decaying over time, there's t time, or x time. Y is my 48 37/100 equals 100 times that value and x is going to be the number of years. So solving for x is just a little bit different than solving for b. We need to use logarithms. We're not going to use powers to undo other powers. We're going to use logarithms to undo exponents. Divide both sides by 100. And then you're going to have the equation in the form of an argument equals a base raised to the x power. Rewrite that as log of the base b of the argument is equal to x. And then the workaround, so you can use log base 10, is that log base 10 of a divided by log base 10 of b equals my exponent, or the number of years that the tree died. How long ago did the tree die? Now, if you're using estimation, you'll note hopefully that 48 and 37/100 is very close to 50. It's less and it's decaying. So if the tree decays, sorry, if carbon-14 has a half-life of 5730 years, this is less than 50%, so it's going to be a little bit more than 5,730, and you should come up with approximately 6,002 years old, 6002. What assumptions are we making? Well, we're assuming that the carbon-14 concentration in the atmosphere has not changed over that 6,000 years, or 6,002 years approximately. Carbon-14 concentration in the atmosphere changes from time to time. The carbon concentration is concentrating currently, it is accelerating, and if you guys follow climate change science, then you understand what I'm saying. With that, I'm going to close with problem number 8, and the next video will be on problem number 9.